10, we're going to really talk about how to go about synthesis with Fennel Rings. There's some tricks that we need to know here that can really help you figure out what to put on first. So for example, if you go through an acylation, this substituent is meta-directing. After you reduce that acyl group here, you get an alkyl group that's ortho-para-directing. If you then go through and oxidize this again, you'll end up with a carboxylic acid, and a carboxylic acid is meta-directing. Which means that say that you end up with a carboxylic acid, but you needed to put an ortho-para substituent, so one here or here, in your synthesis. Then you would go through this process and make sure that you added whatever substituent that you're trying to add to the ortho-para position after you do the reduction and before you do the oxidation here, so that you can direct it as to where it wants to go. A similar type of thing happens with the nitrogen groups, nitrogen containing groups I should say, and these guys are probably used most often. So as you put on the NO2, that guy's meta-directing, and it has issues. So it's meta-directing, very deactivating, and that's the issue. This guy, on the other hand, as soon as you reduce it, is incredibly activating. So it goes from one extreme to the next. And then we go back to a total bad extreme as soon as you add some acid. So there's ways to control things here. And we're going to use those tricks later in the synthesis videos, as well as synthesis problems that you should be trying outside of class. Okay. So what happens if you're actually trying to put on 3 substituents in a particular ring? Well, it gets a little bit complicated. And sometimes the reality is you just gotta run it and see. But essentially, if you have 2 things that agree with each other, like this guy's meta-directing and that guy's meta-directing. So this one is saying, hey, I want you to go over there. And this one's saying, hey, I want you to go over there too. They agree with each other. Bam, that's where you end up with your product here. So then everything's nice and handy and good and everybody agrees with everything. On the other hand, you can have space be an issue. So this guy's an ortho-para director, so is this one, which means that they're both saying go here, right, because that's the ortho position, but then this one's saying here, and this one's saying here, and this one's saying here as well. Notice nobody's saying right there. Okay, so you actually end up with this guy, which is the ortho to this one and para to this one. Good. You end up with this guy, which is the ortho to there and para to the alkyl group there. But this one that's ortho to both of them, there ain't no room there. And there's got to be room for things to come in, and so it doesn't really work very well, and you get very little product there. Say if 2 substituents disagree with which direction they're going to put on a substituent. The reality is that usually the most activating will win. So that's what's going to end up directing. If you ended up having an NH2 and a bromine, for example, that were fighting in their directionalities, the NH2 is probably going to win because he's more strongly activating. Okay. Now, Diazonium salts are like the coolest thing ever. And they end up not only making all the azo dyes that we see as really, really pretty stuff, which I'll show you how to make in just a second, but these guys can be replaced very easily. And so we use them a lot. Here's what we do. You put on NH2, which means that you have to start with HNO3 and H2SO4 to put on your NO2. Then reduce the NO2 to get your NH2. Then add NaNO2, HCl, gotta be cold, and you get this. Now, sometimes they can be explosive, so you have to watch out, but just to let you know. N2Cl is a salt because we've got a positive negative. It can do all this stuff. So I'm going to go backwards. I'm going to go right to left. Copper bromide or CuCl, you end up getting a bromine or a Cl, which you say, I can already do that. You might be able to, but you can't really direct the NO2 pathway as easily. You'll see what I mean when we get to synthesis. You can also get a CN, so that's how to get a cyano group on there. You can get an iodo or a fluoro group with Ki or HBF4. You can actually make a phenol. There's two reaction conditions that are pretty easy to use here. H3O+, that's the easiest one to remember. Or you can use Cu2O with CuNO32 and water. H3PO2 just makes the entire thing go away. And it doesn't really disappear. Hydrogen is the thing that replaces this diazonium salt, obviously. But you can actually direct an entire synthesis with that NO2 or NH2, turn it into a diazonium salt, and then allow it to disappear. Or it looks as if it disappeared. And then if you add it to some type of thing like this, you can end up making those azo dyes. Okay, the mechanism here is a little bit more complex. We start with the NO2. Notice that does have a negative charge to it here. It's going to come grab a hydrogen from the Cl. I'm sorry, from the HCl, and the Cl leaves. And once it's got one, it's still not happy. It goes and takes another one, giving you this NO positive charge here. That's resonance stabilized too. So once it comes in contact with an amine, this nitrogen donates electrons to this electrophile, giving you something like this. So we've got a positive charge on the hydrogen. Positive charge on the nitrogen, 2 hydrogen here. A base comes along, removes the hydrogen, puts electrons back to that nitrogen. This is resonance stabilized again. And once you get to that point, my apologies, I left out an arrow. That will put a negative charge here on this oxygen, which can come and grab a hydrogen from an acid. So probably more HCl that we're using there. The base that's left over will probably come and grab that hydrogen. Electrons go back. And then we have a position where, can't even see where I drew this here. Okay. So this OH group will come and grab another hydrogen. Electrons go back. And then finally we have the nitrogen donated electrons in, so this water molecule right here can leave, generating your diazonium salt. And there's a lot of really cool stuff, as I said, that it can do. So once you have this diazonium salt, it basically opens up a ton of extra synthetic pathways for you. It is worth mention, but I don't want you to get into a habit of falling back on this. But it is worth a mention that there's an SN-AR reaction that also happens. And this is an aromatic substitution. It happens under very specific conditions in that you need an electron withdrawing group in the ortho pair position, and you need a halogen on the other side. In this case only, a nucleophile can actually end up replacing that halogen because of the fact that all these resonance structures can happen with the nitro group there only.